Okay, hello everyone. Okay, so we're going to finish up the alternating series test today and do the ratio and root test. I think you will like them. I liked them very much when I learned them in college. I don't know why, I just thought they were pretty cool. Okay, so we've been looking at the alternating series tests. And with the alternating series test, we had to identify UN. As I was looking at the homework on Edfinity, it may actually call it BN. I'm not sure because I was looking at some of the homework and adjusting the quiz. So this is alternating series test. It's of the form -1 to the n plus 1 or -1 to the n minus 1 or -1 to the n. Either way, it goes back and forth from negative, positive, or positive, negative. So each term in the series switches sign. In order to determine if an alternating series converges, three conditions must be satisfied. That is UN, that is the term that's not included in the alternating part, -1 to the n, has to be positive. UN has to be greater than UN plus 1. In other words, each successive term gets smaller, and we have to show the limit as of UN goes to 0. And so we did a couple of examples. Actually, we did all three of these examples on Tuesday. Okay, so each one we did the test for absolute convergence. And after we determine whether or not the series converge, I am a little bit confused here. There we go. I am on the wrong sheet. Now I'm good. Okay, so after we did this test on this series, we were able to show this series converged. And then we did another test. We were able to show that we could not conclude that this series converged because the UN went to 1. So the conditions of the alternating series test were not satisfied. So we can't conclude that the series converges. And then this last one, we actually ended up writing a function, f of x, being 10x over x squared plus 1. We showed that it was a decreasing function, that is f prime was less than 0. So it's a decreasing function, which meant the series was also decreasing. And then we showed that this limit went to 0. So the next thing after we did that, we looked at the test for absolute convergence. And so for the test for absolute convergence, we basically said, if you look at the sum of the absolute value of the terms, if that series converges, then the original series converges absolutely. And so the example that we looked at this series -1 to the n over n plus 1. When we looked at taking the absolute value of this, so our term was -1 to the n over n plus 1 squared. And this was the absolute value here. So we looked at the absolute value of this term. So that was the absolute value. And when we looked at the absolute value of that term, let me just go back down to here. It skipped. There we go. So when we looked at the absolute value of that term, we were able to show that that series was a P series. So it converged, which meant the original series converged absolutely. And we also showed that another series, summation sine of n over n to the 4th, converged absolutely. And our last example we had was -1 to the n over n. And we can use the alternating series test again to show that that series converges. And then we actually did the test of absolute convergence on this, and we were able to show that this absolute value is the harmonic series. And we all know the harmonic series does not converge. So since this does not converge, then we can say this other series does not converge absolutely. But we have a term for series that have that behavior, and that is a series that is convergent, but is not absolutely convergent, is called conditionally convergent, meaning it only converges with the -1 to the n, but when you take the absolute value of the terms, it does not converge. So for this one, this one gets a special name now. So we were looking at this test. We already showed that this thing converged by the alternating series test. Then we looked at the absolute test of absolute convergence and saw that the absolute value was the harmonic series. It didn't converge. So therefore, by the test of conditional convergence, the series converges conditionally. Okay, so that's where we were yesterday, or actually Tuesday. And so there's one last section in this series, which is actually rather cool. And this pertains to the alternating series estimation theorem. Okay, so the alternating series estimation theorem is as follows. Okay, so we're going to assume that we have an alternating, and our alternating series is the sum minus 1 to the n plus 1 times un. Okay, so this is a series going back and forth in terms. So what we want to do is we want to compute, and that should be a capital N. So I'm going to fix that if I can. Delete, yes, I can. Okay, so then what we're going to do is we are going to compute the nth partial sum. Okay, so that is to sum up the first capital N terms. Okay, and then if you sum up the capital N terms, it says, the alternating series estimation theorem says that this sum will approximate the true sum of the series with an error less than the absolute value of the next term. Okay, so we can actually get a good idea of what our series actually sums to if we use the alternating series estimation theorem. Okay, so I have an example. Okay. So here is my example. And so we want to compute the actual sum of this series, okay? Now this series is an easy one. It happens to be a geometric series. So it being a geometric series, I can find what the true sum is. So, but let's just say we didn't know that this was a geometric series. I know it's a geometric series because I can write it as the sum n equals 1 to infinity of -1/2 to the n minus 1. So it has the geometric series form. Here A is 1 and R is -1/2. So by the geometric series test, we know that this series is going to converge. Why? Why do I know that this series is going to converge? I know I got some takers on this one. Why do I know that this, what is the condition for the geometric series to converge?
Would it be because a is greater than 1? I'm sorry, greater than or equal to 0?
Okay, actually, the sum of a geometric series is dependent on R. So do you remember now what the condition is? Caesar.
I'm trying my best to remember right now. Give me a few, sorry.
Okay, no problem, no problem. I'll let you guys think about that. So in the meantime, we know that the sum, so the sum S is the sum of the entire series. Okay, so S for us is the actual sum of the entire series. It is a number. All right, we know it is a number because the series converges. So So that's going to eat, that's some number. It's, a finite number. Okay, so the alternating series test, the estimation theorem, for this problem, it says for n equals 9, find an estimate for the sum of the series. So we need to compute S9. Okay, so let's compute S9. I'm going to actually do that. I'm going to use my OneNote to do it.
I have the
Can I ask a
answer while
question?
it.
Okay, I have two things going on, question and a comment. Yes. Question, Malcolm?
You cut out on mine for a second. So for the geometric series, you said it converged, but why did it converge?
Oh, I was waiting for you to tell me that.
I have
Oh,
the
you didn't.
answer.
Okay, Caesar has the answer, and the answer is?
Because since it is based on the absolute value of R,
Good.
and since it is less than 1, it converges.
Okay, did you get that, Malcolm? So the geometric series converges when the absolute value of the R is less than 1. And the absolute value of negative a half is a half, which is less than 1. So that series is going to converge. Okay, so what does S9 look like? Let's say it is, okay, so we're going to take and we're going to do the first 9 terms. Okay, so when n is 1, we are clearly just going to get something to the 0 power, so that's 1. And then we're going to subtract off the next term. That's when n is 2, we are going to get minus a half. And then the third term is going to be plus 1/4. And then the fourth term is going to be minus 1/8. Then the fifth term is going to be plus 1/16. And then that's 1, 2, 3, 4, 5. The sixth term is going to be negative 1/32. And the seventh term is going to be positive 1/64. And then the eighth term is going to be negative 1/128. And then the next term is going to be positive 1/256. Okay, so we have the first, the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth, and the ninth term. They alternate positive, negative, positive, negative, positive, negative, positive, negative, positive. And the value of this turns out to be 0.66. Okay, so that is the value of S9. So S9 is supposed to be a good approximation to the true value of the series. And in fact, if we compute S10, so our S10 is actually equal to an absolute value. So we're going to need the absolute value. Well, let's figure out S10 first. So S10 is going to be negative, and it's going to be 1/512. Okay, so that is 256 times 2. All right, so that is 0.02, 002. Okay, so once we've done that, I hope you understand this because this is really not a difficult thing to do. And you may be asked to do it on the exam. It says that this thing approximates the real series with an error of less than the next term. So that means, so by the alternating theorem estimation, alternating series, oh my gosh, I can't talk. Alternating series estimation theorem. That says the difference between the true value and the approximated value is less than or equal to the absolute value of the next term, which would be U10. Okay, so the difference between the true value and the approximated value, that's the error, is less than the next, the error is going to be smaller than the next term. Okay, so that's what the theorem says. So that gives for us the absolute value of S minus S9 is less than or equal to, well, S10 is negative 0.002. So this is going to be an absolute value 0.002. Okay, so we all know how to solve an absolute value problem that says negative 0.002 is less than S minus S9. And this is less than or equal to, actually it's strictly less than, it can't be equal to it. And this is 0.002. So therefore the true sum of the series, which is S, is less than S9 plus 0.002, and it's greater than, oh, that should not be an equals, it should be in less sign. And it's greater than S9 plus 0.002. Okay, so that says that S is less than S9, we said was 0.668.
I have a question.
Yes,
Shouldn't it be S9 minus 0.002 is less than S since you have,
yes, this one should be a negative.
okay, making sure, thank you.
Yes, that one should be a negative. I have somebody in the chat. Okay. And this is plus 0.002, and this is greater than S9, which is 0.668 minus 0.002. So I get that the true value of my series is less than 0.670, but it's greater than 0.666. Okay, that's pretty good to be able to tell me how. So I know if I wanted to just get an idea of what the sum of the series is, look at that estimation. That's really, really good. Okay, so that's a really good indicator of what the sum of the series is. Okay, it's a geometric series. We can find the true sum. So since the summation n equal 1 to infinity and of -1 to the n minus 1 over over 2 to the n minus 1 is simply equal to the sum n equals 1 to infinity of -1/2 to the n minus 1 is just a geometric series. We know what S actually equals. Okay, so we know that S is actually equal to A over 1 minus R. So that's 1 over 1 minus -1/2, which is just 2/3. Okay, so we know what the sum is. And notice 2/3, which is 0.66667. Okay, if we keep going, 2/3 fits right in there. So that's a really good estimation using the alternating series estimation theorem. Okay, any questions? Okay, any questions about this theorem? Whoa. Okay. Well, I think I'm going to call that the end of that section and start the next section. So let's just stop the video.